Hello, I decided to do another high altitude balloon flight. As I think I mentioned in my previous video, I still have 3 balloons and enough helium to do one more launch, so why not, eh? But this time, instead of going all sciencey on it, I'm just going to do it for a bit more of a fun thing. And as you're probably already noticing from the display that we're looking at here, there's a bunch of things that are going to be removed and a few things that are going to be added, and from what I can tell so far it's going to end up at almost exactly the same weight. So I'm aiming for about 150 grams, preferably a little bit less, for the payload, because I want to make it as similar as I can to the last flight, so that the data that I collected from the last flight is actually useful in predicting how this one's going to go. So the main thing that's going to be removed was the GSM module, which was largely useless, really, and it required a separate power regulator as well. So yeah, good to have that off. Plus you have to mess around with not SD cards, SIM cards and all that stuff. Yeah, just a nuisance, so it's gone. I'm also taking off one of the barometers. I'm leaving the other one on just mainly as a temperature, because I'm also going to take the main temperature sensors off, the humidity sensor and the accelerometer. So all these things, I have a pretty good idea now of what it's going to be like. And we're adding a little SD camera. This is just one of the little RunCam Micro Swifts, and the RunCam DVR01, which is a very tiny 3.3 volt, I think it is, yeah, DVR that can record from that. And what this video is going to be mostly about is the hotwire cutdown, which is not quite so simple, and it turned out to be actually quite a lot of code if you want to do it nicely like I think I have done it. I was expecting it to be about a dozen lines of code, but it's quite a lot more. So right at the end of this video, if it hasn't gotten too long by that point, we might take a look at the code, otherwise we might not. But like I say, yeah, most of this video is just going to be about testing and experiments for hotwire cutdown system. And I've also made quite a few improvements, or additions at least, to the Android app that's functioning as the ground station. I've taken away the section that was displaying the GSM data, because that's obviously no longer a part of the system, and I've replaced it with a section which is going to try and predict in real time where the balloon will land as accurately as possible. So this is going to use the wind speeds that were measured on the way up and try and sort of calculate using that. As the balloon's going down, it will be continually updating a marker on the map to where it thinks it's going to land, and it should be pretty accurate, I'm hoping. And I've also made it use the HabHub website prediction as well, so it's going to use the internet to pass on the location of the balloon to that website to get their prediction of where it should land. So let's start off by having a look at how this website works, because that'll explain some of the displays that we see on the Android app later on. So the way this works is you select a starting position and a burst altitude at ascent rate and a descent rate. Then you click Run Prediction, and it will calculate how long it's going to take to get to the burst position, and then how long it's going to take to get down, and which way the wind is going to take it during that time. So we'll get 3 sets of points like that. So what I was looking for from this is just the second part, from the burst point to the ground. Where is it going to go? Now you can't actually make this website do that directly, but what you can do, I found, is you can sort of cheese it a little bit by just putting in the altitude as the ascent rate in meters per second. So this is a ridiculous ascent rate, but it works. And when we run a prediction like that, see, we just sort of get the last part of the trip. It doesn't seem to put the burst. I thought it would have put the burst point exactly on here, or very, very close to the start location, because it's only going to take 1 second to get there, right? But as we'll see in a minute, it sort of calculates everything in time intervals of 50 seconds. So I'm guessing this is a 50-second interval, which is why it didn't get immediately to the burst height straight away. So let's have a look at what's going on behind the scenes here in the network tab. So let me just tidy this up a bit. Oh yeah, that's okay. Get rid of that. Alright, so when I run this prediction, there's quite a few separate things going on, but just to keep this a little bit shorter, we'll look at the final result, which is this one here. So there's a Ajax PHP is being called, and we don't need to worry too much about the details there. But the important point is that we get this response here, which is an array of points, and we can copy that and have a look at it in a little bit more convenient format like this. So we'll see that it's an array of strings which can be split by commas, into 4 components. The first is a UTC timestamp, so this is a number of seconds, and you'll see that this is incrementing in 50 seconds constantly every time, like that. Then we have a lat long, which is obviously where the balloon is predicted to be at that time, and the last component is an altitude. So the first one is 0 because that's the launch altitude where it started from, and then you'll see you've jumped immediately up to not quite 15,000 meters that I had in my input, but it's pretty close. And then we'll see that it's coming down, so 13,683, 13,000. Now notice that we've dropped about 600 between these 2 points, but the next one, the next one's almost 600 as well, but if you keep going down, you'll notice that as you get closer to the ground, these distances are less and less. So it's only about 200 meters difference in the last 2 points, and that's because the air gets thicker. So anyway, the main points to note here is that we have a constant time, but a non-constant altitude, and these divisions of altitude are not the same distance vertically. Anyway, so I took that data and I tried to match it up as best I could against the, we're looking at here seconds in the horizontal, so this is 200 seconds, total time of about half an hour, I think that is there, maybe. And this is just the section from 15,000 meters downwards. And the blue dots are what I got in my last balloon flight, and the red dots here are calculated from the CUSF calculator that we just looked at. When, now this is the important point, when you put in the sea level speed of 5.6, so that's the number that you put into here, that number there. So I was changing this number, tweaking it a little bit up and down until I got it so that these graphs overlaid pretty much as exactly as I could get it, which turned out to be 5.6. So that's the reason why I wanted to use the same parachute and the same weight and everything, so I could pretty much say that this was going to be the same as it was last time. Anyway, so I used, over here I have a little bit of code that I used to format. This is actually the Java code that I used directly in the Android app. And it's a bit of a janky way to do it. If you're doing it properly, you'd figure out what what the equation is supposed to be for this, so that you wouldn't have to hard code these literal values here like this to define these. I'm calling them buckets for the altitude. So altitude is split up to height ranges of these non-constant intervals, and I made this go up to 30,000 meters. Although my next balloon flight, I'm only planning to make it about 15,000 or so, just because it took a hell of a long time last time, and I want to just sort of cut it short to do less driving, and just less time overall would be nice. So anyway, hopefully that'll explain what we're about to see on one of the displays on the Android screen now. Okay, here is the app. The RF24 section is unchanged, but instead of the GSM section, we now have the cutdown section. So cutdown time is going to show the time that the balloon detects that it has successfully cut itself down. So it does that by looking at the velocity down value from the GPS, and when it sees a number in the downward direction that's great enough, I think more than 3 meters per second I set it to, then it thinks it's cut itself down, and it declares that everything is good, and it fills in that time, and it will also fill in this location here. Now that's not really necessary anymore. My original plan was just to take this number and assume that the altitude of cutdown was the one that I wanted, and just manually plug those numbers into the website that we just looked at to get a prediction for landing. But I figured that since this tablet has internet capability, and since I already figured out how that website's working behind the scenes, I thought I might as well just get the tablet to do it for me. It's just one less thing you have to juggle when you're chasing around with balloons and stuff on the launch day. So yeah, location's not actually necessary, but it does at least let me see that the balloon thinks it has cut itself down. So tries is the number of tries that it has made to cut itself down. So when this goes to non-zero, it lets me know that the balloon is at least aware that it is above the altitude that it should be attempting to do cut downs. So when it tries, it doesn't just turn the hot wire on permanently. I'm using a little LiPo, and I thought it might be better if it was just doing it a few seconds at a time, so that's why it has tries. Now this next number here, wind, this is a number that lets me know how many wind samples have been taken at each altitude division on the way up. So the first number here, 0, this will be for, well, this is basically 0 altitude. So 0 to 270-ish will be that first number. Then the second number will be 270 to 550-ish. So each number here is an altitude bucket, and as more and more samples are taken, this number will increase, and it will show the number of samples divided by 10 and then capped at 9. So, for example, if this number was showing a 9, it would mean that we had taken at least 90 samples for that section of altitude. So there's a lot of numbers here, and you need a lot of numbers for the number of altitude buckets that I'm using. For example, if I wanted to go up to 15,000 meters, which is around here somewhere, I'd need about 36 of these numbers, or I would expect to see 36 of these numbers showing a non-zero value as the balloon slowly climbed on the way up. And this just lets me see how well or how good an average, because these numbers are being averaged for each bucket, how good the average wind sample is at each altitude. And another thing you need to consider is that you might accidentally do this, and if you do that, then you're going to miss some samples, because we're not looking at all of the data that the balloon knows. We're just looking at whatever we happen to get transmitted to us through the radio, which is possibly not everything. So if there are some zeros in here still, it will mean that we didn't get good radio connection at that point. Anyway, yeah, so to use those, it's actually quite simple. All you need to do is, for example, let's say that you're at 12,000 meters is the current altitude. So this bucket here would be the highest bucket, and then you just look at all of the buckets below that altitude, and you multiply the wind speed that was measured at that altitude, or for that division of altitude, in meters per second, of course. You just multiply that by 50, because that's the number of seconds that it's going to be within that altitude range, and then you just add those all up. That will give you an XY offset in meters from the current balloon position, and then you just convert that to lat long, and then you have the location. So this tab is just showing BMP 280 numbers only, because that's the only sensor that's on there. Oh, it does show battery, of course, as well. So speaking of markers, there are two new options. Let's get that out of the way. Two new options here. So we have landing predictions, which is, well, won't be able to see much here. This is 00 lat long position, so it's in the ocean off the coast of Africa somewhere. But blue is the balloon. But if I touch this, I actually get the CUSF marker, which is purple. So that's the one that will be updated when I push this button here. And there's another one that's yellow, which for some reason is not. They might all be on top of each other, actually. Yeah, I think they're all on top of each other. But there's, oh, there we go. I don't know how I was able to select the second one. But anyway, this yellow one is the predicted position from my wind samples. And my wind samples prediction is going to be continuously updating every few seconds using the latest data. So as the balloon gets closer and closer to the ground, this data will get really, really accurate until the balloon marker and the yellow marker on the map should converge. And yeah, I hope. In contrast, the CUSF one only updates when you push that button, because it just has to do internet access, and I didn't want to hammer their website with requests every few seconds. And we had, I think, one other option here, which is tablet plus wind sample landing prediction, like that. Yeah. And this is probably going to be what I'm looking at in the last few minutes as the balloon approaches, because this will tell me where I am in relation to where it's most likely to be, where it's most likely to land, rather. And the only other thing that's changed here is a button to clear that wind samples array here, which is, this is wind samples data, and I wanted to have an option to clear that before the flight so that it wasn't looking at old data, because that data, it just has a yes-no confirmation. This data, incidentally, needs to be saved to file. You can't just have that in memory because of what I said before about you might accidentally turn the tablet off. Or the other thing I noticed is that with this tablet and with the OTG Android on the go FTDI adapter thing that I use at least, if you pull the plug out and then put it back in again, the app restarts. Like putting the plug in triggers the app to start, but it won't continue running the one that you had. So you'll lose everything that was just in RAM and it'll be gone. So all of these WinSample data will just be totally wiped if I happen to accidentally pull the plug out. So that kind of sucks. So for that reason, these values have to be stored to a file on disk, and that's the reason you need this button to get rid of them from time to time if you want to. At the start of a flight you'd want to do that. Anyway, I think that's all the changes on the app. I'm just doing some testing to see how much current and how much time it takes to cut through this nylon string that I'm going to be using. And what I've discovered is that up to about 2.4 amps, and the current will depend on the thickness of the wire, I think. So the wire I'm using is slightly less than 1 millimeter in diameter, I think. It's definitely less than 1 millimeter, maybe 0.8 millimeters or something like that. But anyway, for that diameter of nichrome wire, 2.4 amps was not actually enough to cut through. 2.8 amps managed to cut through in about 10 seconds or so. You could sort of see it getting slightly softer as it cut through, but it was kind of slow. But what I have it on here now is 3.6 amps, and that will cut through in about 5 seconds, maybe slightly less than 5 seconds. And the voltage required to do that for the length of wire that I'm using is 1.75 volts or so. And currently I'm using, well, this is what I'll probably go for in the end. 5 centimeters should be enough. So for that length of wire, 1.75 volts gives 3.6 amps to cut through in 5 seconds. At room temperature, that is. So if this is running at sort of minus 20 degrees Celsius, way up in the upper atmosphere, it's not going to manage to do that in 5 seconds. So it might have to go a little bit higher, perhaps say 2 volts. And it might take about 10 seconds to get through it. But I think it should still manage to get through it at that voltage and that current. And I like the fact that it can all be done in quite a low voltage. So the 2 volts is around about a 50% duty cycle for a single cell LiPo, which is what I'm planning to use this with. And I like that because I didn't really want to make the LiPo use its full power, because it's going to be sagging a lot at that low temperature anyway. So if it can be done within a sort of a lower duty cycle for the LiPo, it'll be much more likely to work. So anyway, the way I've been testing it is I just use the vice grips to clip a bit of string on there and let it run. So I'll just do one of the runs at 3.6 amps just to show you what it looks like. Okay, this is with 4 amps now, just to see if there's any difference in time. A little bit quicker, eh? Okay, and this is 4.4 amps. I'm expecting this will be about 2 volts. Yep. Oh, a little bit more, but it was nice and quick. That might be what we want, eh? 4.4 amps. So the next thing to check is whether I can do that with a 3.3 volt signal instead of manually switching it off and on there. So you'll see that the power is actually on at the moment, but my wire, which is here, that's my 5 centimeters there, and you can't solder it obviously to the other pieces of wire there because the heat might cause problems, but yeah, so I'm using some screws there, and the power, the reason it's not cutting through right now is because it's being gated by this MOSFET there, and these 2 wires here are the ground and the signal for that, or the gate signal, yeah, and that's a 3.3 volt voltage regulator and a little switch to a 3-cell LiPo. So the idea with this is that when we switch this 3.3 volt signal on for a few seconds, about 4 seconds I guess, oops, a bit smoky there. Okay, now I'm doing the same thing except with an Arduino Pro Mini 3.3 volt one there, and that's going to be opening the gate for the larger current to come through. And this is set to a maximum voltage of 4, and it's on. And current limit's at 5.4, but what I'm doing here is, instead of just simply turning it on, I'm using a PWM pulse, and I tried a pulse of 100, so that's 100 out of a total of 255 maximum, so you know, just under half, and that gave me just over 2 amps, so I set it to 200, and that's giving me 4.4 amps, which is exactly what I wanted. So anyway, just to demonstrate that, so when I push the button here, it's going to wait for 5 seconds, and then it's going to turn it on for 3 seconds, which last time I tried it was enough to cut through. So let's see if it works. Yep. And we were too far away to see there, but that should have been about 4.4 amps. So the next test I want to try is with this. Now this is not the battery that I'm going to use. This is probably about twice as big as what I want, but as you can maybe see on there it says 800, so this is 800 milliamps. So for this battery, 4 amps is about 5C. So it's pretty manageable, I think. For a battery half this size, 4 amps would be 10C, which is still, should be okay. Okay, next test. This side is the same as before, and over here now, instead of using that power supply, I'm using the little LiPo, and I wanted to see how much the voltage sagged as well, so I have the voltage on another meter, and this one's hopefully going to show us current. I haven't tried this yet, so not sure what's going to happen, but hopefully it will cut through and the battery won't sag too much. 3, 4, 5, go. Cut through 3.8 amps, and the battery does not seem to have been bothered by it much at all. That's great. Alright, so that went fairly well. So that's 800 milliamp hour. I tried with this one as well. This is 600 milliamp hour. It was basically the same. Now, these are more like the kind of battery that I actually wanted to use with this, because they are like 7 or 8 grams versus these, which are, well, that one's about 20 grams. So it's just a little bit on the heavy side, I think. So I'm going to give it a shot with this one now, and I'm not expecting that to go so well, but let's see what happens. 5, go. It's not even getting past about 1.2 amps, and it didn't cut through. Okay, now let's try with this one. 5, go. Ugh. The battery's not sagging much, really, is it? Maybe it's not making a good connection somewhere. Maybe this is my problem. 5, go. That's a bit better. Yep, it cut through. Okay, so I guess it was just a bad connection somewhere there. So what I changed there is I just took out the ammeter that was in series with the circuit. So I think these alligator clips weren't really helping me much. They don't make a very good connection. But that's promising. So that was this battery. Looks like that might work. Let's go back to this one again, since now that my connections are better, that one might work as well. Okay, trying this one now. By the way, since I've started using the batteries for this, I changed the time from 3 seconds to 4 seconds to account for the fact that none of them are fully charged. I'm using them all at storage charge here. Anyway, I think this one will probably work. Let's see what happens. Yep, only just though. So that one sagged. I don't know if you can see that, but it got down to 2.8 volts there, which is not bad, really. I mean, I'm quite surprised at how well these little things do at room temperature. Let's remember, at room temperature. Okay, I got this in the mail today. This is another parachute from randomaerospace.co.uk. As I said in my previous videos, a little bit expensive, but very nice quality. I didn't really want to spend that much again, but I do want to make sure that the drag of the parachute is going to be the same as it was last time. Otherwise, my previous flight will not be much use for predictions of how this one's going to go. So what I'm going to do next is a drop test from the Hexacopter. So I've set up this little test bed. There's the stuff in there. I'm just going to use that little LiPo to power the actual circuit. And then over here I have a single cell LiPo, that's the 800 milliamp hour one there. And just a switch there so I can disconnect that if I need to. And up here, this is what I'm planning to use on the final balloon. Just a little piece of 2mm or 2.5mm plywood, and again some screws there to make that circuit work, and the radio's sticking out the back there. So I'm just going to do a little drop test here inside with a hard-coded timer, and then I'll try this on the Hexacopter tomorrow. Perfect. Oh, no, not perfect. It went red hot there for a second, eh? I haven't seen that before, but at least... Oh, it's turned off, so that's alright. That's the first time I've seen it go red hot, and I'm not exactly sure why. Okay, the next thing I want to confirm is whether the code that handles the hot wire cutting will correctly detect when the wire has been cut, or the cord has been cut, and it starts to fall. So it's looking for a downward movement of 3 meters per second or more, and I can't really do that inside because it needs to fall, you know, quite a distance. So I'm going to hang it on the bottom of the Hexacopter, and I've set the height for 160 meters. That's not 160 meters above here, because remember that's height above sea level. So height above sea level here is about 110 meters. The tanks up there are about 120, so I'm guessing that 160 will be about twice the height of the trees there. I don't really want it to go too high because it might not, you know, I don't want it to end up in the trees or on the roof or anything. So 160 meters should be about 50 meters above where I'm standing, somewhere around there. And there's not too much wind, so it's a good time to do it. And parachute, so that's the one that's going to be cut. And I've hung the parachute so that hopefully when it falls it will go like that, and the GPS will still remain facing upwards, which doesn't really matter too much. So what we're looking for, if everything works correctly, in the onboard log on the SD card here, we want to see that it only attempted to cut the cord once, and it has a maximum time of 6 seconds to cut through. But we're expecting it to only take about 3 or 4 seconds. So what I'd like to see is that it does not use the full 6 seconds to cut through, and it stops at about, say, 3 or 4 seconds. That's what I really want to see. It doesn't really matter too much, because if it doesn't work, it just means that this battery is going to be working harder than it should. And if by some strange chance it's falling and all the way down, this battery is still trying to cut through using the hot wire, that it doesn't really matter too much, but the battery will obviously be ruined by that. But more than that, it's just kind of clumsy to not do it efficiently. So being a software programmer by trade, I kind of feel like I should try and make it do it a bit smarter than just the dumbest way. So anyway, enough talk. Let's get this going. Right, let's save some time and cut to the chase, because that first test there didn't work, but it does let us see what happens in the log. So this is the onboard log that we're looking at here, and we'll see that it did at least, you know, record some information, and it did detect that it had not worked. So that's what the failed is signifying there. And it didn't start at 160, it started at 170, because there's actually a 10-second delay that I put in, and it's probably not really necessary in flight, but the reason I put that in was because in my testing I was making use of the fact that that steep hill next to my house is quite handy for an altitude change of a few meters. I think about 4 or 5 meters or so I can get just by walking up and down that hill. So I was using that hill to do some preliminary testing in the early stages, and I found that you could get a GPS fix with a 3D fix, so the GPS thought it had a good fix, but the altitude was still a few meters off, and that would give me some false positives. So I just put a 10-second timeout so that it would not turn the hot wire on within 10 seconds of having been below the target altitude. Anyway, so 170 it failed, 195 it failed. So we have a bunch of failed attempts here. and then you can see the altitude coming back down. So 102, it's back on the ground, I think. So let's see what happened. The LiPo is fine. Well, I have absolutely no idea. I've just spent about 10 minutes looking at the code. There's absolutely nothing I can see in the code that would have stopped that from working. The only code path... Oh, what's this here? Oh, that would do it, wouldn't it? Look at that. Solder's pulled off of there. Okay. Alright, I soldered that up, so let's try this again. I actually soldered that up yesterday because it looks suspicious, and somehow it just keeps breaking. Unfortunately, we've lost a lot of daylight now, so you're probably going to have a hard time seeing anything in the hat cam. So we might just have to show you the down-facing camera on the Hex, and hopefully it'll catch something. So I did not reset the Arduino, which means that it's probably still showing 7, I think was the number of tries that it made last time. So for this test we want to see it go to 8, but no further. Okay, we just hit 60 meters, so it should be about 10 seconds from now. Oh, I think it's going to go over into the... There we go. Look at that. Oh, it's going to land right there, I think. No? Where is it going? Nice placement, eh? So it's right there. Beautiful. Okay, so the log for that event looked like this. It was exactly what I wanted to see. One and only one attempt, and instead of having a 6-second, like the full length of time that we allowed, it was only on for 2.5 seconds. So this is milliseconds here, and that means that it detected the falling state quite quickly, and it was able to turn off the hot wire, and that was the last time we saw any attempts being made. So that's just right. Alright, this video is getting a little bit longer than I wanted, so I won't be showing you any source code. I will upload it to my site, of course, and give you the link if you want to look at it. But just before I finish, I wanted to discuss a couple of concerns that may be arising in the viewers, and I can just see some comments now if I don't say something about this. One is that I'm using this wire to support the weight of the payload, and more typically what you see is that you'll have the cable directly supporting the payload, and the nichrome wire will come in from the side and it'll be sort of coiled around the cable and cut through it in the same sort of way. And if this was a big heavy balloon with a heavy payload, I would of course be more inclined to do it that way. Well, I'd pretty much have to do it that way. But the reason I can get away with doing this is because I'm only dealing with 150 grams or so total weight here, and this wire is more than capable of doing that, so that's fine. But it does suffer, at least if I have this much wire, so that's 5 centimeters or so, it can move around like that, and if it's doing that for an hour or so, it might break, right? It's not the end of the world because we want it to break anyway, but it might not make it as high as we wanted it to, so that could still be a problem. But I have an idea that will probably solve that, and it's related to another problem that we have, which is how to arrange the parachute on the way up. So ideally, the best situation is the way I did it last time, with the parachute being here, the balloon is up the top, and the payload is at the bottom. And that's fine if you're going all the way and you're just going to let the balloon pop. But if you want to cut it down, ideally you want to cut it there. But that's a bit of a problem because the battery and everything and the hot wire is going to be here. So if you wanted to cut this connection above the parachute, you'd have to have a big long wire coming up here with the nichrome up here, and it's just not really that manageable. But what's nice about that situation is that when you're going up, the parachute's kind of nice and closed like that, so it's not catching the wind very much, and it's not slowing you down as you're moving in that direction. So another way you could arrange that is obviously like the way I did it today. You have the payload in the middle and the parachute sort of trailing on the way up like this. And that's easy, very simple to do. Took me just a few minutes to sort of string everything to get this done, and it works. What's not so great about it is that the parachute is causing drag, It's kind of exaggerated a little bit here because the Hexacopter is blowing a lot of wind down, so I don't think the parachute would be open quite that much on the way up, but nevertheless it would be causing a lot more drag like this than it would be if it was nicely closed in between the balloon and the payload. The other problem with this is that it's going to be causing the wind, the horizontal wind, to have much more of an effect than it would if it was nicely closed. And another inconvenience that we have with this arrangement is that if you attach the parachute to the bottom of your payload here, that keeps it out of the way of the hot wire, so the cable between the parachute and payload is not going to be in danger of being cut, let's hope. But it means that on the way down, the payload is going to be upside down. So if you have your GPS on the top, as you would have if you're smart like me, on the way down, it's going to be on the bottom, which is, it probably still work. These little GPSs are pretty good, but it's not ideal. So what you might try and do is what I did today, just to see if it would cause any problems, and connect your parachute to the top in the same vicinity as the hot wire. So yeah, not very good, and you can see why that is also a bit of an issue. So here's my cunning plan that I came up with to get around all of those issues. Well, I haven't tried it yet, but it seems like it should work. So the hot wire will actually be inside the enclosure. This is not really that important, I don't think. It should be able to get hot enough within 6 seconds. Like, it got red hot within 4 seconds, just like yesterday when I tried it. So even at that cold altitude, it shouldn't really be an issue. But nevertheless, it will be beneficial, if anything, for it to be inside the enclosure, which is about 20 to 26 degrees warmer than outside. So this is the cord that goes up to the balloon, and that's going to be coming in here through not one hole but 2 holes, as I'll point out why this is important in a minute. This orange thing over here is the parachute, and it has 2 little loops at the top of the parachute, which is where I was, lifting it up by with the balloon before. So I figured I could probably put these loops through this loop of the main cord, so that when the main cord, the blue one here, is cut, this will slip out and up, and this loop will no longer exist. So the parachute, which is going to be sort of sitting on the side of the payload like that, this is the zoomed out view on the right there, this point here should now be freed. And the other nice thing about this is that because the hot wire is inside, we can connect the string from the parachute to the top of the box without having to worry about the hot wire cutting this string. So all in all, it works out fairly nice, and on the way up the parachute will be closed like this, so it shouldn't be catching the wind too much. I mean, it's going to be able to open at the bottom as the wind flaps it around a bit, so it will be a little bit more draggy than in the ideal situation where the parachute is in between the payload and the balloon. But all things considered, I don't know if you could really do a whole lot better. So one thing that's sort of bugging me a bit is this antenna that I have sticking out the side for the NRF24 module. It kind of has to be sticking out the side like that, but it occurred to me that it doesn't need to have that hard plastic whip antenna casing around it, so I'll probably take that off. So this antenna will not be rigid, it will be floppy, so hopefully the string will just be able to pull over it, and it will just boing, bounce back again. At least that's the idea. So what do you think? I haven't tried this yet. This will be what I try at the beginning of my next video, I think. But anyway, that will be another time because this one's got way too long. Thanks for watching. See you next time. But wait, there's more. Sorry, I forgot to explain why it's important for there to be 2 holes here instead of just 1, and there needs to be a little bit of separation there is really the point. And I also forgot to point out that because the hot wire is inside like this and the cable that's going up to the balloon is being guided through these holes, it means that there's not really any way for the hot wire to be getting swayed and bent backwards and forwards as it goes up, because this wire, I've drawn it as a sort of a curved shape here, but it's pretty much just going to be going straight to the holes like that. And because it's under tension, yeah, it's just not going to be flapping around. So there should be much less fatigue on the nichrome wire in this situation. So why is it important to have 2 holes? Well, take a look at this. I think I probably did about 15, 16 tests of this wire cutting or string cutting, and in every single case this happened. So this is a wire that was cut, and yet I could probably break it if I... Yeah, okay, so I can break it there, but it was joined fairly strongly, and I was expecting the one that I did today, hanging underneath the Hexacopter, not to do that, but it did it. So even this one did it. It's joined, not quite as well as that other one, but nevertheless it is joined up again. So I think the reason that that happens is that when the weight is on the string like this, so let's say this hoop here is where the hot wire is going through. The hot wire is the diameter is very small. It's less than 1 millimeter. So what happens is you get the string pulling like that, and the two strands of the string going upwards on the right hand side there are pretty much parallel. So when the nylon gets hot and softens, the hot wire just sort of pulls through it and it closes again on the other side. I was quite surprised to see that that happened every single time. So to avoid that, you might want to have a little bit of space between these, so that when this cord is cut, these two strands of wire here, or string here, are not just going directly upwards together. They need to be getting pulled in a slightly different direction, and that should make sure that we don't get the nylon sticking together on the way out, because we need we need to make sure that this hoop has nothing left to hold it there after the after the altitude is, after this cord is cut. This one has to be cut through as well. Anyway, I think you get the idea. So now the video is finished. Thank you for watching the extra part. Bye.